Looking across transport, looking across heat and generation, it's evident at the moment that we are going far too slow. In transport, according to the government's Committee on Climate Change, we're going to need 300,000 EV charging stations by 2030. As of June this year, we have just over 30,000. It's a huge gap. What that means in practice is that we need to install an average of 40,000 chargers per year between now and 2030. But as of June this year, it's 30,000. We're evidently not going fast enough. In the last 2 years, we've installed only 10,000 chargers, nowhere near 40,000. Across heating, the situation is perhaps at its worst. By 2050, we're going to need almost all homes to be heated from low carbon sources. But right now, less than 5% are actually heated this way. And there are record numbers of gas boilers going in year on year, whilst heat pump numbers sit in the tens of thousands. What that means in practice for planners is that between now and 2050, just looking at existing building stock, 1 million homes are going to need to transition every single year. And many of those homes are going to require substantial retrofit in order to become suitable for items like heat pumps, something I'll talk about a little bit more later. Third and finally, renewable generation. Obviously, this is the area that the UK is arguably performing best in. In fact, the UK has one of the lowest carbon grids in the world. Last year, 45.5% of UK electricity came from low carbon sources, which is a great number, very good, but it's a hard path to reach net zero. As we electrify transport and as we electrify heating, more and more demand is going to be put on that electricity system. Grid constraints and weather variability mean that low carbon power is often not available where and when it's needed, making it really tricky to decarbonize when you're in the last few percent. And we could need as much as 600 terawatt hours of low carbon power to meet forecast demand by 2050. It's going to be a tall order to get there. And at the moment, the authority for that energy transition sits firmly with local government. What that means is that local government is somehow going to need to find the resource, the expertise, the funding, the data, the information that they need in order to build credible plans to take a local region from where it is now, a long way from net zero, to something close to or at net zero by either 2050 or sooner. We've been working with a number of local authorities over the past year to try to figure out what the key challenges are, what the key blockers are, and what can be done to accelerate that. I'll cover off what can be done to accelerate it in a minute, but first off, I think it's valuable to try and understand what it is the key blockers are. We were lucky enough to be funded by BEIS through the Modernising Energy Data Applications Task Force to run a large-scale user research drive, speaking to distribution network operators, local authorities, consultants, and practitioners who are all involved in this local energy transition. We spoke to them to understand what it is they do on the day-to-day, and they ran us through their workflows of project inception, design, delivery, and final implementation. We also made the effort to go and speak to most local authorities in the UK who have so far had full-scale local area energy plans done, or carbon plans, to discuss and understand what the challenges were they faced in implementation once that was in place. As you can see from here, there was a varied response, but some general trends emerged. One of the core problems across all three groups was access to data. Now, that covered a whole breadth of things, but the three core areas in data that really were challenging across all these groups was number one, accessing building level data, specifically understanding what capacity a building has for either retrofit or new technologies, and understanding what the energy demand profile of that building is right now, and what it would be if changes were made to it in the future. That's critical for local authorities and practitioners in order to build out a business case for new technologies, but it's also critical for network operators who need to understand how demands are impacting the network today, but also up into the future in order to reinforce appropriately. One of the second areas that I want to highlight today that's a real challenge across all three groups is a pretty simple one, but it's collaboration. At the moment, it's the local authority's responsibility, but as has been noted by the Energy Systems Catapult in their best practice guidelines, and really by anyone who's doing this in practice, it's got to be a collaborative effort. It's got to be a collaborative effort from the local authority, from the network operator who manages the infrastructure across gas and electricity, and from the consultants or practitioners or OEM providers that get brought in to supply specific technologies. But at the moment, this is something that is extremely difficult. "It's all Greek to me" was quite a common quote I'd hear from local authorities trying to understand network operator language. It was difficult for them. And that's one of the most jarring distinctions. But even within an organization, working across teams is very difficult. An EV team within a local authority often will have absolutely no idea what's happening in heating, what's happening in retrofit or social housing. Generally, at the moment, the process lacks the cohesion needed to build out a strategic whole systems plan. In short, there's an urgent need for two things. For one, increased visibility and data access. And by that, I mean getting the data at the right level of granularity, to the right level of accuracy, in the right area that you need, and not waiting months to get that. And there's also an urgent need for an ability or a tool that can facilitate this kind of collaboration and data sharing across different stakeholder groups. Apologies, this is a bit of a dense slide. I'll maybe take a moment in a minute so that you can actually read some of these quotes, but I wanted to include some of the words from actual local authorities, actual consultants, actual practitioners who we've spoken to and worked with. You get the sense of what's coming across here, and I'll just give you guys a minute to take a look at these. So what's the cost of all of these problems and all these challenges? Well, it's a lot of frustrated organizations, obviously, but there's also a financial cost and a time cost. I want to highlight three figures that came out of the research that we've done. The first is that because data is not readily available, an enormous amount of time is spent repeating modeling project on project on project. For a heat feasibility study, an average cost of 10,000 was spent just modeling data, modeling baseline basic data. That means infilling gaps in EPC records, and that means modeling energy demand profiles primarily. Now that's £10,000 replicated project by project by project. That's not the way it should be happening. This data should be readily available on demand, and it shouldn't be modeled on a project by project basis because that's not financially viable. Similarly, sticking with the financials, up to £700,000 have been spent by local authorities and combined authorities commissioning local area energy plans in the last 5 years. We spoke to many of these teams, and they are facing huge challenges to implement those plans. One of the biggest challenges they have is that local area energy plans are very regional and they're very suggestive. So they'll take a location or an area of a city and recommend installing heat pumps in that area. But what it doesn't give you is the building level data and the granularity of data you actually need to plan, which is to say which buildings are actually suitable for heat pumps, which curbsides are suitable for EV charge points, which rooftops could take rooftop PV, and what's the capacity in the network to support this. All of that information doesn't exist in a LAEP. And at the moment, almost every local authority we've spoken to who's trying to implement a LAEP is facing huge challenges, not least because the data that they do have access to was out of date very soon after the LAEP was published. I think one of the most interesting quotes on here for me is the last at the bottom, which says a local area energy plan is out of date the second you click enter on the keyboard. And that's a common problem we find, even where the data is available, it's quickly out of date and there's not the infrastructure in place to update it. Finally, and I promise after this I'll finish with the down talk and move on to something a bit more interesting and some of the solutions that we want to discuss today. But third and finally, once you've got your data in place, once you've got your plan in place, once your collaborators are there, your consultants are there, you have a network connection that's typically required. If you want to install a heat pump either in a domestic property or maybe you want to install a charge point on the street, there's going to be a need to connect to the electricity network to support that. Now, this process at the moment is working better in some DNOs than in others, and there's a lot of exciting innovation going around to try to facilitate and accelerate it. However, historically to date, it has been a big challenge for either local authorities or private developers to get the information they need about network capacities ahead of submitting that connection request. And by that, I mean that they usually have to submit a connection request in order to understand if there's even capacity on the network where they're trying to connect. There's rarely, and there are some exceptions with some DNOs, but there's rarely an opportunity to do things like search or filter or triage sites based on network capacity. What that means in practice is that from all of the interviews that we conducted, about 30% of all the projects we surveyed were cancelled after a connection request had been submitted because the DNO connection costs made the project financially non-viable. And by that, I mean the connection cost was simply too high to support the business case. Now, that's a cancellation that's happened late. It's happened after a feasibility study's already been conducted in most cases, and after a connection request has gone through. So that can mean tens of thousands of pounds spent and wasted assessing site suitability for a project where the DNO connection cost was already going to be too high to actually connect. So looking across these three areas, there are three that I want to highlight where I think we've found in our experience that digital solutions and cloud-based solutions specifically can stand to rapidly accelerate progress. And I want to talk about a couple of the examples that we've been developing and a couple of the use cases we've been working on. Now, those are around accessing data, so clearing up licensing issues, modeling data at the right level of granularity and making it available to local area energy planners, be they in local authorities or private developers or DNOs. The second is in using that data and utilizing that to then turn these strategic targets or these local area energy plans into short lists of projects. And by that, I mean geolocated projects where you can say it's this building, it's this UPRN, or these street corners where I know I could actually install a technology. And third and finally, connecting to the network and ways that we've been exploring with SSEN, how we might be able to accelerate this process. So what we've been doing is we've been developing a tool called Local Area Energy Planner Plus, LAEP Plus. It's a collaborative web-based mapping and design tool that helps stakeholders from across all these different groups come together to plan and develop new energy systems. We've recently moved out of the beta phase and we're moving into more of a live rollout, but what I'm going to talk about is a couple of the innovation projects that we've run trialing LAEP Plus. As you can see from here, LAEP Plus is web-based, cloud-based, and what that means is that the data can be kept up to date, it can be shared across different groups, and it can be visualized, overlaid, and brought together in one place. Some of the different ways we've been using that are around citing EV charge points and heat pumps and insulation. Instead of using videos because they're not rendering very well today, I'm actually going to switch over to doing a live demo and talk a bit around some of the different use cases we've been developing. So first I want to look at Brighton and Hove City Council area. This is where we worked with a consultant called EV Charging, who are an all-round solutions provider for EV chargers who typically work with local authorities, but also sometimes private developers, to try to find the best locations to site EV charge points and support their installation. We worked with them for 6 months to try to understand what their core challenges were, what data they needed, and where the biggest blockers were. Now, they found that 30% of their projects would typically be discounted because of site design. What that means is basic things like the presence of on-street furniture, street lamps, for example, that you can see here, or because the area was in a zone of flood risk, or potentially because the pavement didn't meet safety requirements for an on-street charge point. For example, a pavement that's 2 meters or less is typically rendered unsafe for an on-street charger due to the risk of trip hazards. Now, what they found was that these 30% of projects that were unsuitable, they would often spend hours and hours of time from a project manager's point of view, which would cost tens of thousands over the year, going to site visits to assess and see whether this pavement or that pavement, this car park or this region was actually suitable. They wouldn't tend to know where to start. They'd often start from a local authority's long list of, say, 1,000 sites, and then pick a more manageable chunk from there of 100 to then go and visit through site visits. Now, this was a problem they recognized because it meant that they were spending hours and hours traveling to locations, visiting them and assessing them, and not necessarily even picking the best locations at the end. So what we did was we brought in these data layers into this tool for them to use to try to triage those sites, filter them more effectively and quicker. The benefit for them was they spent less time as a practitioner visiting sites. For the local authority, it meant they got a much quicker turnaround and much better locations for their charge points. And of course, for the network operator in the region, it meant that the connection requests that came through had been better triaged and better assessed, and were less likely to be cancelled due to things like site design or connection costs. So what we did was we brought in information around where you can't put an EV, where you could put an EV, and where you should put an EV. What that means is looking at what we've already covered, the presence of street furniture that might be obstructive, flood risks or pavement width that might restrict the safety standards. But it also means bringing in things like traffic data sets to understand where you have the greatest intensity of vehicles and where you might have a good opportunity to site an EV charge point. Train stations and taxi ranks were extremely useful for them to understand because these are prime locations where vehicles are regularly stopped for 30 minutes or more. And these sorts of locations would be ideal for EV charging. However, they're a national company. They don't have time to search every single city, every single place to understand where the best opportunities are. So we brought that in for them in a couple of input data layers, which talk around where you have these prime opportunities, where you have existing bus routes, where you have existing transport corridors, all of which start to build up a picture of where you can actually site EV charge points practically, but also where you should, where there's the greatest need, where there are transport deficits at the moment. That includes a whole range of input data sets that came from the local authority and were shared on the same platform by them. But it also includes a number of modeled data sets that we brought in, looking, for example, at things like forecast utilization. This was something we developed in order to allow consultants like EV charging to understand where they should put EVs and what the profit they might make off that would be, which obviously helps when making a decision around not just where to put an EV charge point, but also where you should put things like slow or ultra fast charge points. You don't want to waste money installing an ultra charge point in a domestic area where it's not going to be used very often, or where you might have a car parked for 8 hours. Another very replicable data set that again is the sort of digital solution that can accelerate these things is looking at another area, which is public transport accessibility. Where this is relevant for EVs, I'll come to in a moment. But first off, what actually is public transport accessibility levels? This was a data set that was developed for London and Greater Manchester to look at scoring regions of approximately 100 meters squared on an index which dictates how well connected a region is to public transport vectors. So how well connected you are to buses, to trains, to other routes. Essentially, if you live in the far north of Scotland, your PTAL score is going to be extremely low. Whereas if you live in the ultra low emission zone in London, your PTAL score is very high. Where this comes in for things like EV charge points or an electric transport transition is you understand that where there's low PTAL scores, you're much more likely to have high vehicle ownership and therefore high EV ownership. And from a local authority's point of view, it's also very valuable to understand where you have things like transport poverty, so you can target that and understand that. Similarly, we brought in a range of data sets around demographics, household income, street furniture, and building stock in order to help understand not just the need for the curbside charges that I've spoken about, but also domestic charges. This was really critical for things like network operators who we've spoken to around sharing data and the challenges they have around predicting where you're likely to have EV uptake domestically and where you're likely to see greatest demand. Because obviously if something like 100 charge points goes in one area, that can cause significant strain on the network. So again, we brought in a lot of data sets which can be easily replicated nationally to do this modeling, to do it quickly, and to do it in the browser. As I said, LEAP Plus hasn't just been trialed for transport, although that has been one of the most fast-moving areas in the past year across the energy transition. We've also been using it to target some of the slower areas, some of the ones that are maybe less interesting, but can make a real difference at the moment at a time like this, where we're already going into a cost of living crisis and energy costs are skyrocketing. And that's at looking at things like insulation and looking at different ways that we can improve warmth within homes. So the second example that I want to talk about today is one that's really important at the moment, and that's looking at how you could make homes warmer for low-income households. So in this example here, what we're doing is we're looking at building stock rather than transport data sets to understand across, in this case, Dundee City, which buildings might be suitable for sustainable warmth funding. And what that means is we're looking for buildings that don't have insulation or have limited insulation or subpar insulation, typically buildings that are EPC D or below. And we're also looking for homes that are in low income areas. So that typically means income of around 30,000 or less. So what I can do using LEAP Plus in this case is bring in all of this building stock data set and start to filter it in order to identify the best homes. So in this case, because I'm looking at sustainable warmth, I'm interested in insulation type. I'm interested specifically in buildings that don't have insulation. So cavity uninsulated or solid wall uninsulated. And as you can see, that's filtered about 70,000 buildings down to 20,000. On top of that, I'm interested in adding in income data so that I can target areas where there is a lot of fuel poverty. And to do that, we can do things like bring in information on open source information on the Scottish Index of Multiple Deprivation, which provides an indication of likely income, or we could bring in some council data or some data sets from other sources such as PropTech or FinTech, Experian, in order to understand household income on a much more granular level. And what you can see that we've done here is we've taken that 70,000 buildings down to a short list of approximately 10,000, which meet those criteria. That's something that can then be exported, it can be shared, it can be saved within the same interface and have others brought in. That took me about a minute, but at the moment, this is analysis that's commonly done by consultants, and it's consultant work that can take several weeks and tens of thousands of pounds, which is not the best use of the time of very intelligent people who could obviously offer substantially more value later on in the project, or could add in additional data sets, additional modeling and resource. This kind of very replicable analysis, it's not something that most consultants actually want to spend a lot of time doing. It's a lot of Excel work, it's a lot of grunt work. Whereas if you bring it into tools like LEAP Plus, that's something that can be done much, much quicker. It's obviously also not just about the building stock. What we can do as well is understand things like network capacity, one of the key blockers that I mentioned earlier. In this case, in Dundee, we have access to quite a lot of network data because we're happy to be working with SSEN as part of Project RESOP. And what this means we can do is we can link up UPRNs and buildings with the LV network data around it and start to understand what the capacity would be or what the impact on the network would be if we brought in new technologies. And that's possible to do at the feeder level, at the LV, and if we zoom out, you can also see HV. What this enables local authorities or private contractors to do is very quickly start to filter out regions where there's likely to be a slower connection, a more difficult connection, or a potentially more expensive connection. Now, in some cases, obviously, this network, the network will need to be reinforced anyway, but in other cases, it can be valuable. For example, if I was looking to site an EV charge point on this street, from my point of view as a local authority or a private contractor, there's very little difference between siting it slightly further south versus slightly further north. And if that results in a quicker and an easier connection, that's a decision that in our experience, local authorities are very happy to make. So again, the benefit of bringing all this data in is that it's a much quicker outcome and much easier to do. So that's the electricity network. Obviously, not all of the transition will necessarily move on to electrified heating. So it is also possible at the moment with data that's out there, with data that's available, to understand potential for hydrogen. This is still a work in progress in a lot of areas, but what I've just brought up here is some of the best data that's around at the moment, which is looking at the gas network pipes. So if I zoom in again, you'll be able to see. And what this allows you to do is then also consider not just electrified heating, but also gas and the potential for hydrogen heating. So for example, I can filter these additional cables here by looking at which ones are suitable for hydrogen. In this case, which ones might be plastic, for example, or already have existing capacity. And from a quick filter there, it looks like the majority of the pipes around this area would be suitable for hydrogen. From Dundee's point of view, that's an interesting indication and an idea that they may be able to go and speak to the gas operator in the area, SGN, to discuss what their future plans are for hydrogen, what they consider hydrogen ready, and whether they would be considering doing something in this area. From Dundee's point of view, this is a much quicker way to triage, and it's a much easier way to triage. Skipping through a couple of the slides that weren't quite rendering then. I also want to talk a little bit around where we're going next and some of the big challenges that we're facing with data at the moment. And then I'll wrap up in some time for some questions. So next stage for a lot of these projects will be trying to understand the network connection. And that's where I want to talk about some of the work that we're doing at the moment as part of Project RESOP and as part of the Bayes Smart Meter Repository. There's some really interesting work going on at the moment trying to solve the final challenge that I mentioned when we were discussing what the key blockers were to low-tire energy planning. And one of the key ones was understanding energy demand, and specifically energy demand at the building level and at half-hourly intervals. Because currently what's done for most modeling tools and most simulations is looking at peaks. What that means is understanding what peak demand or peak generation is going to be over the course of a year. So for PV, for example, that might be the peak on a summer's day. Or for a heat pump, that would be a peak on a winter's day. What that means, however, is that you end up with very conservative modeling going on, because if you're only ever training based on peaks, you don't necessarily understand how close to the wire you are and how long a period in the year you'd be asking a feeder cable or a substation to operate at max capacity, because in most cases, most can go over. So what we're doing as part of Project RESOP is bringing together a wide array of these planning data sets I've been talking about, but also building out some of the capabilities for local authorities and for private developers like Dundee, like other organizations, to come in and actually create some of those network connections themselves, what you can see here on the right-hand side. What that means is you can log in, you can click on an asset, you can select PV, you can select EV charge points and drag and drop that onto the network and connect it there live in the tool. What that does is pings an API, which sends a signal to a power flow modeling tool being used by SSEN, which can run an assessment on how likely it is that asset might overload that network and quickly send back information so that users can understand what the impact of that connection would be on the network and what's the potential outcome of a connection inquiry would be. This isn't necessarily replacing the connection inquiry process, but it is allowing them to triage and understand what the likely connection outcome would be at different sites. At the moment, we're doing that with ADMDs, but as I said, we're working towards moving that into half-hourly profiles as part of a project under the Bayes Smart Meter Data Repository. I'll pause there because we are at time.